Hey folks, welcome back for another stop on our tour of AP statistics. Today we're talking about section 1.3, describing quantitative data with numbers. Let's just review real quick. In section 1.2, let me go all the back. Actually, let me go back to 1.1. 1.1 we did describing categorical data with graphs. And then in section 1.2, we switched our discussion to quantitative data. And we were still talking about graphs. That's where we learned about the dot plot and the stem plot and the histogram. Today, we're going to continue talking about quantitative data, but we're going to be describing distributions with numbers. And in fact, we'll even introduce another type of graph that has to do with those descriptive numbers of a quantitative distribution. First thing we'll talk about is the mean of a set of observations. And you've been calculating the mean since, I don't know, 5th or 6th grade, maybe even longer ago than that. Basically, you add up all the numbers and divide by the total number of observations. So remember, n is the number of observations. Don't forget the Greek letter sigma in math we use to represent a sum. And this here, x with a bar over the top, it's got a really funky name. You'll never figure out what this is. We call it x bar. So the mean of a distribution, the symbol for that is x with a bar over the top, and we call that x bar. All right, so median of a distribution, that's another one that you've been, you've probably done in earlier grades. Median is the midpoint of a distribution. It's the number such that about half of the observations are smaller and about half are larger. Now, I've been using the median in some of our previous lessons. I just didn't call it that. I said, let's find the center of the distribution, and I counted to find when I had the same number of observations above and below that point. To find the median of a distribution, it's tedious to do by hand. Our calculators will do it for us practically instantaneously, but it's important to know how it's done. So the median of a distribution is found by arranging the observations from smallest to largest. And then you have to decide if the distribution has an odd number or an even number. If it's odd, it's the middle observation, the center observation in the ordered list. But if it's an even numbered distribution, then you have to take the average of the two center observations in the ordered list. Last thing here is the term resistant measure. A statistic, which in the things that we're calculating here, mean and median, those are statistics. A statistic that is not affected very much by extreme observation. So a couple things here. What's an extreme observation? An extreme observation is one that's very different than most of them in the distribution. And then last but not least, it says here not affected very much. And for those of you that are exact, you're not going to like that language because the term very much is not an exact value. Can't quantify that. We're just going to say that if we have two different statistics and one is affected more by extreme observations than the other, we'll say that that statistic is less resistant to extreme observations than the other statistics. And we'll see examples of that here shortly. Okay, let's jump right into an example now. We're going to be talking about McDonald's beef sandwiches. Here's a list that shows Big Mac, cheeseburger, daily double, ... all the way down to quarter pounder with cheese. And I believe quarter pounder with cheese. I believe over in Europe they call that a Royale with cheese. But what we're measuring here is the amount of fat in grams for each of these sandwiches. First thing we have to do here is calculate the mean and median for the distribution. Well, I have some helpful information for us here. First of all, I have the list, and let's just see. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We got 12 different sandwiches in this distribution. In fact, if I had read a little more carefully, I would have noticed it says that right in the problem. This list is not in order, though, but My stem plot is in order, so it's going to be real easy for me to find the median here. Now, the distribution has an even number of observations, so I'm going to look for the 6th and 7th value in the distribution and then average those two. So if the number of observations n is even, the median is the average of the two center observations. So that would be the 6th and the 7th. So let's find those. 1, 2, 3, 4, 5, 6, 7. So the 6th and 7th observation are both 26. So that means the median of the distribution is 26. And a lot of times you will see the letter capital M for median, 26 grams of fat. Okay, so now let's find the mean. So the mean of the distribution, I've got to find out what the sum of all of those different values are for those 12 different sandwiches. And I did that offline, folks. I'm just going to tell you it's 298. So the sum of that column of values there is 298. So let's see, the mean is going to be 298 divided by 12 observations, and we grip it and rip it in our calculator. We'll round that to a couple decimals. That gives me 24.83 grams. So there's our mean and median for the distribution. Now we can move on to part B. Part B, whoa, look at that double quarter pounder with cheese. It weighs in at a gut-busting 43 grams of fat. Perhaps it's an outlier. Recalculate the mean and median of the distribution without this value. Okay, so let's talk about the median first. So the median value, if I get rid of the 12th observation, the 43, so I'm just going to kind of scratch that out here. If I get rid of this one, then let's talk about what happens. Well, now we have only 11 observations in the distribution, so the median would be the 6th. There'd be 5 below, 5 above, plus the 6th one. So that's going to be 1, 2, 3, 4, 5. That's going to be this value right here. So the median without the 43 is 26 grams of fat. So interestingly enough, it did not change. So the median before and after we remove that unusually large observation is the same. Now let's talk about the mean. So I had 298 grams of fat before, and now I'm going to subtract out 43 from that. That gives me 255. Okay, and I don't have 12 observations anymore. I only have 11. So go ahead and rip it on our calculator. It gives me 23.18 grams of fat. So I now have if I take out that extremely high observation, I have a mean that is considerably lower than it was before. So it was 24.83 before, and now it's only 23.18 once I remove that unusually high observation. So let's see if we can learn anything about the term resistant measure from this last example. You'll notice our median did not change, but our mean did change. The mean without the high observation was much lower. So let's see what we can conclude here. The observation of 43 grams of fat increases the mean, but has no effect on the median. The median resists the pull of the unusually high observation, but the mean does not. The mean is not a resistant measure of center. Okay, let's talk about this real quick. So the median had no effect whatsoever when we removed the 43. That doesn't mean if you remove a high observation, it'll never have an effect on the median. Just in this case, it didn't, because again, I had those two values of 26 right in the middle there. So when I removed that high one, I still had a median of 26. But again, let's look at the mean. We went from 24.83 grams to 23.18, and that's over a full gram of fat difference. That was that high fat sandwich made the mean look worse than it was without that high value. Okay, so let's talk about some things that I think you should remember about mean versus median. So some comments about mean versus median. First of all, they both are a measure of center, and that's included at the top of the notes, but I think I forgot to mention that. So you notice here it says definitions, measuring center. So mean and median are both measures of the center of a distribution. And that was worth mentioning because I forgot to mention it before. So what else can we say about mean versus median? The mean and median of a symmetric distribution will be similar. In fact, for a perfectly symmetric distribution, they will be equal. So let's take a perfectly symmetric distribution. Like let's say I have two values in the distribution. Let's say I have 2 and 4. So those are my two observations. I got two measurements there, 2 and 4. Well, the median of those would just be the middle of that because I have an even number of observations. I just have to average the middle two there. So the average of 2 and 4 is 3. So for this distribution, the median is 3. Well, what about the mean? Well, the mean is how I just add those two up. 4 plus 2 divided by 2, that's 6 divided by 2, or 3. So again, if your distribution is perfectly symmetric, your mean and your median will be exactly the same. Okay, another comment here. The mean is pulled toward the long tail in a skewed distribution. The median is not pulled as much as the mean. So that's why, again, not real exact language here. I said it's not pulled as much. And the reason why I'm saying that is because the median is still affected by unusually high observations. It's just not affected as much as the mean. Okay, last thing I want to mention here is the median is a better measure of center than the mean for a skewed distribution. So anytime we're working with skewed distributions and I ask you what's the center of the distribution, you should automatically be using the median rather than the mean. Okay, so that's it for page 1 of the notes here. Let's go ahead and shut it down and start page 2 in another video.